Hello pre-calc students, here we are with basic differentiation rules, and we've been in 18.1 consistently using this definition, this limit definition of the derivative, but it becomes tedious and boring, so I'm going to give you some derivative rules to make the whole process much simpler. First, the constant rule. Basically, if fx equals a constant, you've essentially just got a horizontal line, and horizontal lines always have a slope of 0. So the slope of the tangent line at any point of a constant function is 0. So f of x equals 42, the derivative is just 0. Okay. Second rule, power rule. If f of x equals x to the n, and n is an integer, then the derivative is n times x to the n minus 1. Well, we'll prove it in a second. Let's just do this example here. F prime of x, then, we bring the power down in front and lower the power by 1. 3 times x to the 3 minus 1, which is 3x squared. In the proof, you can see where this is coming from. Now remember, the derivative is going to be the limit as h goes to 0 of f of x plus h, so that's x plus h to the n minus x to the n minus f of x all over h. I get our n's and h's confused here. So it's the limit as h goes to 0. We don't want to evaluate the limit yet. We'll just get x to the n minus x to the n and be 0 over 0. So we're going to expand this out. X to the n plus n times x to the n minus 1 h to the 1 using our binomial expansion plus n times n minus 1 all over 2 x to the n minus 2 h squared plus yada 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 all the way down to x, the other end will be h to the n. And then all of that was basically x plus h to the n, and then you're going to subtract off x to the n all over h. Now the key thing here is that the x to the n's cancel out. That's why it doesn't show up in the derivative rule. And everything else now has at least one h in it. Look at the h's here. There's an h there, there's an h squared there, h to the n there. So when we divide through by h into each of these terms, you'll end up with n x to the n minus 1, the h drops out there, plus n times n minus 1 over 2 x to the n minus 2 times h, plus all the way up to h to the n minus 1. And you can see that basically all these terms still have an h, this term doesn't. So that's how you get n x to the n minus 1. It's that second term in from the binomial expansion. Okay. Now, f of x equals c times x to the n, where c is a real number and n is an integer. Then the derivative is c times n to the x to the n minus 1. So in other words, to pull out the constant rule. And basically, you could do this even more general too. If you take a constant times a function, you're just going to end up bringing that constant along for the ride because the constant can essentially factor out. See, if I just came over here and put the c into here, you could factor the c out, and there would be c in front of the limit. Okay, so let's apply it here. So for the derivative now, f prime of x, the constant comes along for the ride. You might want to first think of a cube root of x as x to the 1/3. Now we can write as 1/3 x to the 1/3 minus 1. So it's 5/3 x to the negative 2/3. You can stop there. Usually, I like to put something in the form of what I originally saw it in. It was in radical form, so I'm going to put the final answer in radical form. I'm going to put the x underneath as positive 2/3, so the cube root of x squared, and write it like that. Now the derivative of sum equals the sum of the derivatives. The derivative of difference equals the difference in derivatives. That comes in very handy when we're doing polynomials, so we can just cruise along here and take the derivative of each part. The derivative of x to the 5th is 5x to the 4th. 4x cubed would be 4, the constant comes along for I, times 3 times x to the 2, minus 4, because this is x to the 1, so when the 1 comes down in front, you just get a 0 there, and it disappears. The derivative of 2 is 0. Now what's the derivative of pi to the 7th? A lot of kids mistakenly say 7 pi to the 6th. No, pi is not a variable, it's a constant. So that's just 0 as well. So we get for the derivative 5x to the 4th plus 12x squared minus 4. Notice with a polynomial function, you always drop a degree in the derivative. What's the derivative of the sine? Let's start by actually looking at some of these slopes and try and think of the derivative that way. That if this is the original function, y equals f of x, when we look at this, the function's increasing here, so all the tangent lines we draw will have a positive slope. And then it's decreasing, so then they'll have a negative slope. And in this section it's increasing, so the derivative becomes positive again. Notice right here, the derivative is clearly 0 because the slope of the tangent line is 0. And down here. We can also see that this whole section here is concave down, concave down. That means the slopes are changing and they're decreasing. And the whole section here is concave up, so it's increasing. And if we estimate the slope right here, I'd say it's about 1. Notice how what we said before, when you graph the sine wave, don't aim right for that peak. You'll get that duck shape. That's all obnoxious and wrong. Aim about 50% higher than the peak up here, because as you go over to pi over 2, that's going to be up at about pi over 2. So it's a slope of 1 about there. And notice, conversely, then you got a slope of negative 1 down here. And then you return to a slope of 1 again. Does that remind you of something? I hope it does. It's the cosine. The derivative is the cosine of x. If the original function is the sine, the derivative is the cosine. Now that's just sort of a visual proof. A more formal proof then involves the squeeze theorem. And we'll do that right now. Know all these derivative rules. The derivative of the sine is the cosine. The derivative of the cosine, though, is the opposite of the sine, because notice here we're decreasing here, so we actually start off negative. And it keeps oscillating back and forth like that. The derivative of the tangent is the secant squared. We'll prove that after we do the quotient rule. Cosecant is negative cosecant cotangent. Secant is secant tangent. Derivative of the cotangent is negative cosecant squared x. Notice that whenever you take the derivative of a co-trig function, you end up with a negative factor. Here's the formal proof of the derivative of the sine. Remember, it's going to be the limit as h goes to 0 of the sine of x plus h, that's f of x plus h, minus the sine of x all over h. Okay, we're going to need a little more space here, clearly. So it's the limit as h goes to 0. Can't evaluate the limit now, we'll just get the sine of x minus sine x over 0, so we get 0 over 0. So you have to expand it out. Remember, we memorized those expansions with the sine. Sine x cosine h minus cosine x sine h minus the sine x all over h. So it's limit as h goes to 0. Now I do a little clever grouping here. I'm going to put the things that have the sine x together, plus the limit as h goes to 0 of, actually, minus, make that a minus, minus the limit as h goes to 0 of cosine x sine h all over h. Okay? And then keep factoring out here the limit as h goes to 0 of, I'm going to take the sine x out of these two, times the limit as h goes to 0 of cosine h minus 1 all over h, minus the limit as h goes to 0. Oh, I'm so sorry. Sine of x plus h is an addition in between these two. So this is still a minus, but this is a plus in here. Limit as h goes to 0 of the cosine of x times the limit as h goes to 0 of sine h over h. Now, recall some of our trig limits. All of this is 0. That was a special trig limit. Along with this limit as h goes to 0 of sine h over h, that's 1. And the limit as h goes to 0 of the sine of x is just the sine of x. You get the sine of x times 0 plus the cosine of x times 1, and that's how you get cosine x, QED. The derivative of the sine is the cosine. And we didn't use the squeeze theorem. We used the squeeze theorem to prove this limit. So we used some of our special trig limits. Okay, now the applications of derivatives come up a lot with velocity. Consider a positive function, h of t or s of t. Both those can be used for position, height, or s for displacement of an object. The velocity of the object at time t equals c is given by velocity is the derivative of height, or the derivative of displacement. And so it's back to this limit definition or this limit definition. Those look like the alternative definitions. That's to give you the idea of the average rate of change turning into the instantaneous rate of change. So the instantaneous rate of change equals the limit as t goes to c as the 2 points to come together of the average rate of change. Now the height of a ball is thrown upwards from 30 feet above the ground is given by the position function like this. Now notice, you might recall from physics with negative 1/2 gt squared plus initial velocity times time plus initial height. Well, if you put the gravitational acceleration of negative 32 in there, you'll get the there should be a plus in here. You'll get the negative 16. It's 1/2 gt squared plus initial velocity times time plus height, and g is given as a negative quantity because it's going down. And then you put the initial velocity of 50, so that's where the 50t comes from. Initial height of 30, that's where the 30 comes from. And here's a graph that I did on GeoGebra. You can try and get this on your calculators, right, on your TI-89s. The window is the key thing. You can look kind of forward ahead here to see what's the velocity of 2 to get an idea of how you should scale up the window. You can also think in terms of the y's. You're going to start at 30, and actually it's being thrown up, so you're going to have to go higher than 30. Now, when does the ball hit the ground? Okay, so the question is, when is the height, s of t, equal to 0? So we set 0 equal to negative 16 squared plus 50t plus 30, or 0 equals, let's divide through by negative 2, 8t squared minus 25t minus 15. And we can check b squared minus 4ac to see if that's positive or negative, and ends up being b squared minus 4ac. B squared minus 4ac ends up equaling 1105. That's not a perfect square, so we can't factor it. So we go to the quadratic formula. 25 plus or minus the square root of 1105 over 16. And one answer is 25 plus the square root of 1105 over 16, and you get 3.64, or you get time equals, if we do the minus answer, negative 0.5, 2. And you can see how, from our picture, the 3.64 makes a lot of sense. That's one right there. That's where it hits the ground. This negative 0.52 doesn't seem to make sense because it goes back in the past. But it's like the ball got shot up from a height of 30. The algebra is telling you this other answer down here. So we're just going to keep this one. When does it hit the ground? Later there. Now let's keep our poster up here while we go on to look at another one. Pin that down, pin that down, pin that down. And let's look at our second question. C, what is the velocity of the ball 2 seconds after it's thrown? And we're going to do this in two ways. The velocity of the ball 2 seconds after it's thrown. So some of you might remember from physics a velocity equation that final velocity equals initial velocity plus acceleration times time. So you take the initial velocity, which was 50 feet per second, take the acceleration, which is negative 32 feet per second, times the time of 2 seconds. 50 plus negative 64 is negative 14 feet per second. That was from physics. Now in calculus, which is the basis of physics, we can come up with a velocity equals the derivative of the displacement. So you take your velocity, your displacement equation. Remember, displacement was negative 16t squared plus 50t plus 30, and take the first derivative. So that becomes negative 32t plus 50. And notice how it's the same thing as this. And then you find the velocity at time 2 seconds, negative 32 times 2 plus 50, negative 64 plus 50, negative 14 feet per second. Okay? So I don't expect you to memorize physics equations. I do expect you to memorize this concept that the velocity is the derivative of displacement. and acceleration is the derivative of velocity. Now what's the terminal velocity of the ball? That's the velocity of the ball just before it hits the ground here. So we can put in a time of 3.64 seconds into the equation we just developed here of negative 32t plus 50 for the velocity. So velocity equals negative 32t plus 50. So negative 32 times 3.64, and I'm going to get all the digits off my calculator, plus 50. And so we have negative 32 times the answer we got from before, which is roughly 3.64, plus 50. And we get negative 66. Negative 66.48 feet per second. Notice it's negative because it's going in the downward direction. Okay, now this is an entirely different equation. Find the equation of a tangent line to f of x at x to the 6 minus 4x cubed plus 3 when x equals 2. So you can visually get an idea of this. Let me unpin this. We can look at a picture I did of a GeoGebra. You can do this on your calculator as well. I had to do a lot of scale changes to get the idea of what's going on with these bumps. And to get the equation of the tangent line at x equals 2, we're going to have to figure out two things. What's this point here at x equals 2? And what's the slope of that line? And then we can use point slope to put it all together. So let's first of all find the slope. Find the slope, which is going to equal the derivative at x equals 2. So f prime of x is 6x to the 5th minus 12x squared plus nothing. And then to find f prime of 2, we can use synthetic substitution, or actually in this case we just use direct substitution because there's only two terms. 6 times 2 to the 5th minus 12 times 2 squared, and 6 times 32 minus 12 times 4, 180, and 12 is 192, minus 48, and we get 144. That's the slope of the tangent line equals 144. That's what the calculus tells you. Now we also have to come up with a point at x equals 2. Now I'm going to go back to using synthetic substitution here. Put 2 into the original function f of x. We have to find f of 2 now. So that's 1, 0, 0, x to the 5th, x to the 4th, negative 4, 0, 0 for squared term, first degree term, and 3. So multiplying by 2 is pretty straightforward. 2 times 2 is 4, 4, 8, 4, 8, 8, 16, 16, 32, 35. And something is amiss here, because this is telling me definitely negative 253. So let's find the mistake. X to the 6th minus 4x cubed plus 3. 1, the 6th, 5th, 4th, 3rd power, 2nd, 1st, constant term. Putting the 2. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 4. 4 times 2 is 8. 8. 16. 16 times 2 is 32. 35. Why is this? Oh, we're not quite done yet. That's right. So we get the point 2 comma 35, which does seem to agree with this over here. 2 comma 35. And this hugely intense slope of 144. Remember, the scaling got changed here. You might think, oh, that's only like a slope of over 1 up 6, but notice the scaling factor here. So now we use point slope to say y minus 35 equals 144 times x minus 2. So you get y minus 35 equals 144, x minus 288, and then add 35 to both sides, 144x minus 253. Now I'd accept this answer too. Point slope form, perfectly legit for giving me an equation for the tangent line. Okay, that's it. Flange out.